All right, if you're an engineer, you know there's a huge difference between textbook theory and what actually happens out in the field. Well, today, we're going to bridge that gap when it comes to power cables. We're going to get you up to speed on the stuff that really matters when you're on the job. So, let's dive in.
So let's kick things off with a bit of a puzzle. It sounds kind of weird, right? But the answer to this question gets to the very heart of real-world cable design. It's one of those things that separates what you learn in school from what you need to know in practice. Don't worry, we're going to unravel this mystery as we go. Here's the game plan for today. First, we'll talk about how cables are identified, their language basically. Then we'll dive inside the conductor to really get a grip on resistance. After that, we'll uncover these invisible AC effects that completely change the game. And finally, we'll see how it all adds up to energy loss.
Okay, Section 1, Voltage Designations. Look, before you can do anything with a cable, you have to speak its language, and that all starts with its voltage rating.
So in the real world, we use this U0 over U designation. It's simple, but it's precise. U0 is just the voltage between a conductor and the ground. U is the voltage between any two of the phase conductors. This is the professional standard for specifying exactly what a cable is built to handle.
And here's what that looks like in the wild, with some common British standards. Take that 6350/11,000 volt cable, for example. It's designed for 11,000 volts between phases, and it can handle 6,350 volts from any single phase to the earth. Getting this right isn't just a good idea. It's absolutely non-negotiable for safety and performance.
And this is why that precision is so critical. You just can't rely on vague terms like medium voltage or MV. Why? Because it can mean totally different things depending on where you are or what standard you're using. You can see right here how different it can be. So the big takeaway? To avoid dangerous, expensive mistakes, you have to use the specific U0 over U rating every single time.
All right, on to Section 2, the reality of resistance. Now that we know how to identify the cable, let's get inside it and look at the conductor itself. You know, the fundamental opposition to current. But as you're about to see, it's a little more complicated than just plain old Ohm's law.
With direct current, or DC, resistance is our starting point. It's our baseline. It's determined by the conductor's material and how it's all put together. And as you can see from the formula, it changes pretty predictably with temperature. Basically, as things get hotter, resistance goes up. Simple enough, right? This is ground zero.
But here it is, the big question for any power engineer. What happens when that current is constantly flipping back and forth? Because in the real world, we almost always deal with alternating current, or AC. And the moment that current starts oscillating, well, simple DC resistance just doesn't tell you the whole story anymore. Okay, Section 3, the invisible AC effects. So with AC, these two invisible phenomena pop up, and they're the answer to that puzzle we started with. Let's meet our two invisible enemies, the skin effect and the proximity effect.
Let's get our definition straight first. The skin effect, think of that as an internal thing. It's where the AC current avoids the center of the wire and prefers to flow along the outer surface, or its skin. The proximity effect, on the other hand, is external. It's all about how the magnetic field from a cable next door messes with the current flow in your cable. So, why does this happen? It all comes down to magnetic fields. For the skin effect, the conductor's own magnetic field is strongest right at its core. This creates a higher opposition to the current, what we call impedance, that literally pushes the current outward. For the proximity effect, the field from the wire next to it actually shoves the current over to one side. It's physics in action, and the result is that both of these effects increase the effective resistance of the cable. So that brings us to Section 4, electrical losses. Okay, so who cares if the current hangs out on the edge of the wire? Well, you should, because it generates heat. And in any power system, heat is just wasted energy. It's wasted money. This is where we talk about electrical losses. When a cable is actually doing its job, carrying a load, the heat it gives off, its losses, can be broken down into three main buckets. You've got losses right in the conductor, losses in the insulation, which we call the dielectric, and losses in the metallic sheath or shield.
So those conductor losses, they are a direct result of what we just talked about. The skin and proximity effects force all that current into a smaller area, which cranks up the AC resistance. And what does more resistance mean? More heat. And more heat means more power lost. This is where that abstract physics hits your bottom line hard.
But hold on, the losses don't just stop at the conductor. The insulation, the dielectric, it generates heat too. And that metallic sheath around the cable, it can act like the second part of a transformer, with unwanted currents getting induced in it from the main conductor's magnetic field. These are called eddy and circuit currents. And yep, they create their own heat, adding to the total energy loss.
Now, this is absolutely crucial. While conductor losses are usually your biggest problem at lower voltages, these dielectric losses, they become a huge deal in high voltage systems. As you can see from the quote, as that voltage climbs, these losses just take off, rising super rapidly. You absolutely have to factor them into your designs.
So there you have it. We've gone from a cable's official name to the invisible physics happening inside it, all the way to the real-world heat and energy it loses. Understanding all this isn't just about passing a test, it's the foundation for designing efficient, reliable, and safe power systems. The main takeaway is that every single choice you make, from the voltage rating to how far apart you space the cables, has a consequence. So the real question is, how are you going to use what you've learned to cut down on waste in your next project?